All right, let's dive into one of those things that's happening all around us and even inside of us every single second, but you probably never even see it. We're talking about chemical equilibrium. It's this incredible unseen balancing act that basically runs the world. So let's get into it. Okay, so let me ask you something. Ever wonder why a brand new sealed bottle of soda is just packed with fizz, but the second you open it, it's kind of on a countdown to going flat? What's the deal with that? Well, believe it or not, the answer is chemical equilibrium. And stick with me, because by the end of this, you're going to totally get it. So first things first, we got to get this idea out of our heads that chemical reactions are just a one-way street. You mix A and B, you get C, and that's it, show's over. But in reality, a whole lot of them are actually two-way streets. They can go forwards and backwards. So check this out. On the left, you've got your classic irreversible reaction. Think of it like burning wood. Once it's ash, it's ash. It's not turning back into a log. But on the right, that's where the magic happens. See that special double arrow? That means it's reversible. Hydrogen and iodine can team up to become hydrogen iodide, sure, but that hydrogen iodide can also decide to break up and go right back to being hydrogen and iodine. This constant back and forth, that is the key to everything. Okay, so you might be thinking, if everything is just going forwards and backwards all the time, does anything ever really get done? And that's a great question. The answer is yes. Eventually, it finds this perfect sweet spot, a point of dynamic balance. And that sweet spot is what we call chemical equilibrium. Now, the most important word here is dynamic. This does not mean the reaction has stopped. Not at all. Think about it like a really busy bridge during rush hour. You've got the exact same number of cars coming into the city as you have leaving it. The traffic is still flowing like crazy in both directions, but the total number of cars in the city, it stays perfectly constant. That's chemical equilibrium in a nutshell. So for this whole balancing act to work, there are a few ground rules. For one, it has to happen in a closed system. Nothing can get in or out. Think of our sealed soda bottle. Once equilibrium is hit, the amounts of all the chemicals involved, the reactants and the products, they lock in and stay constant. And remember, it's always dynamic. The forward and reverse reactions are still chugging along at the same pace. And what's really cool is, it doesn't matter if you start with all reactants or all products, you'll eventually end up at the same balance point. All right, so now we know what equilibrium is, but the next question is, can we predict it? Or even better, can we control it? Can we bend it to our will? You bet we can. There are rules to this game, and once you know them, you're in the driver's seat. First up is something called the equilibrium constant, or Kc for short. Honestly, the easiest way to think about this is like a scorecard for the reaction. It's a super simple ratio. You just take the amount of products you have and divide it by the amount of reactants. This one little number tells you the entire story of where the balance point is. And reading the scorecard is super straightforward. If your Kc is a big number, bigger than 1, it means the products are winning. The reaction really favors making products. If Kc is a tiny number, less than 1, then the reactants are in the driver's seat. The reaction prefers to stay on the left side. And if it's somewhere around 1, well, then it's a pretty even split down the middle. Easy, right? Okay, but now for the real powerhouse, the master rule of the game. It's called Chatellier's principle, and it's basically a superpower for chemists. Here's the core idea. If you have a system that's happily in equilibrium, and you mess with it, you poke it, you disturb it, it's going to shift itself to undo what you just did. It's like a really stubborn seesaw. You push one side down, and the whole system is going to work to level itself back out. It always fights back to find balance. And this isn't just some neat textbook theory. This principle is a total game changer, and we use it to control reactions that literally change the world on a massive scale. Let me introduce you to the Haber process. This one reaction right here, it's arguably one of the most important chemical reactions in all of human history. It takes nitrogen from the air and turns it into ammonia, which is the main ingredient in fertilizer that feeds billions of people. It's a huge deal. And pay close attention to that little plus heat on the right side. That's a product too. And it's a crucial clue for what's coming next. So, here's the puzzle. If you're running a massive chemical plant, you don't want a 50-50 balance. You want to make as much ammonia as you possibly can. So, how can we use Le Chatelier's principle, that stubborn seesaw, to force this reaction to make more of what we want? Well, here's the genius of it. First, you crank up the pressure. A lot. Now, look at the equation. On the left, you've got 4 molecules of gas. But on the right, only 2. The system is feeling squeezed, so to relieve that pressure, it shifts to the side with fewer gas molecules. boom, it shifts to the right, making more ammonia for us. Next, remember that heat was a product? We can treat it like any other product. If we pull heat out by cooling the system down, the reaction will say, hey, where'd my heat go? And it'll shift to the right to produce more heat. And in the process, it makes more ammonia for us too. It's an absolutely brilliant way to manipulate the system. Okay, so the Haber process is this huge, world-changing example. But this balancing act isn't just for giant factories. It's happening all around you, all the time, in ways you might not even realize. And that brings us right back to where we started, that fizzy drink. Inside that sealed bottle, there's a ton of pressure, and that pressure forces carbon dioxide gas to dissolve into the liquid. They're in equilibrium, but the moment you twist that cap, psst, you release all that pressure. The system is disturbed. So what does it do? Le Chatelier's principle kicks in. To fight against that drop in pressure, the equilibrium shifts to the left, turning the dissolved CO2 back into a gas to try and build the pressure back up. And that's your fizz. That's the gas escaping. So you see, this is everywhere. It's in the massive factories making fertilizer. It's in the simple pleasure of a carbonated drink. And it's even inside you, right now. The way your blood carries oxygen from your lungs to your cells depends on a super delicate equilibrium between oxygen and hemoglobin. It is this constant, invisible, and absolutely essential balancing act. So that kind of leaves us with one final big thought. I mean, if our own bodies are relying on these perfect chemical balances just to function from one second to the next, what other invisible, dynamic balancing acts are out there silently shaping our entire world right now? It's pretty amazing to think about. Thanks for tuning in.